Welcome! Today we're diving into one of the most fundamental parts of physics, the thermal properties of matter. You know how it can be kind of tricky to remember the difference between heat and temperature? Or maybe that ideal gas law just looks a little intimidating. Well, don't worry, we're going to clear all of that up right here, right now.
So, here's our game plan. First, we'll tackle the basics. Then, we'll get into that famous ideal gas law. After that, we'll see how things literally get bigger when they get hot, and we'll finish everything off with a quick quiz to make sure it all sticks. Ready? Let's do this. All right, first things first. Let's tackle the one thing that trips up so many people. Heat versus temperature. I know, in everyday life we use them almost interchangeably. But in physics, they are two totally different concepts, and nailing this difference is your first big step. So what is the real story here? Are they the same thing, or is there some crucial difference you absolutely need to know for your exam? Okay, here's the absolute key. Think of temperature as a property of an object. It's basically a number that tells us how much the tiny molecules inside that object are jiggling and vibrating around. The faster they jiggle, the higher the temperature. Now, heat. Heat is different. Heat isn't something an object has, it's energy that's moving. It's the energy that flows from a hotter thing to a colder thing. So, an object has a temperature, but it transfers heat. Let me give you a perfect example. Picture a hot cup of tea. Its molecules are going absolutely crazy. That's a high temperature. The air in the room is cooler, its molecules are much calmer. So what happens? Energy starts to flow from that hyperactive tea into the calmer air. That flow, that energy in transit, that's heat. And it keeps flowing until the tea and the air are at the exact same temperature. We call that reaching thermal equilibrium. Okay, so we get what temperature is, all that molecular jiggling, but how do we actually put a number on it? You're going to run into three main scales. They were all set up using different reference points, usually the freezing and boiling points of water. But I'll give you a hint. For physics, one of these is the undisputed champion. That's right, it's Kelvin. And we're about to see exactly why it's so important. Now check this out. This is a really neat little trick. Look at Celsius and Kelvin. The difference between freezing and boiling water is 100 degrees for Celsius, and it's also 100 units for Kelvin. This is awesome. It means the size of 1 degree Celsius is exactly the same as 1 Kelvin, and that makes converting between them super easy. So what makes the Kelvin scale so special? Well, it starts at the coldest possible temperature in the entire universe, absolute zero. At 0 Kelvin, that's minus 273.15 degrees Celsius. All that molecular jiggling we keep talking about basically just stops. It's the ultimate point of stillness. You can't get any colder than that. And here it is, the one formula you really need to memorize. To switch from Celsius to Kelvin, you just add 273.15. And it's so important because a lot of physics equations, especially the big one we're about to meet, they just won't work unless you use an absolute temperature scale. They need that true zero starting point that only Kelvin gives you. All right, let's switch gears and talk about gases. It turns out the way a gas behaves, its pressure, its volume, its temperature, it's not random at all. It's all connected by one simple but incredibly powerful equation. This right here, this is the ideal gas law. It's an absolute cornerstone of thermodynamics. What's so cool about it is that it links all the key properties of a gas together. If you know a few things about a gas, you can use this law to figure out the rest. It's like a secret code for how gases work. So let's just quickly break down what's what. P is for pressure, V is for volume, and T, you guessed it, is the absolute temperature, and it has to be in Kelvin. Mu is just how much gas you have, and R is just a special number called the universal gas constant that makes all the math work out perfectly. Now, this law didn't just appear out of nowhere, right? It was actually built from a couple of simpler observations. You had Boyle's law, which basically says if you squish a gas into a smaller box, its molecules are going to bounce off the walls more often, and that means higher pressure. Then you have Charles's law, which says if you heat up a gas, its molecules get more energy, move faster, and push outwards, making the volume bigger. The ideal gas law just brilliantly combines both of those ideas into one single powerful formula. Okay, so we've talked gases. But what about solids and liquids? Well, they react to heat too. And you have definitely seen this in action. We call it thermal expansion. I mean, think about this for a second. The blacksmith has a solid iron ring that's actually too small to fit on the wheel. So how in the world do they get it on there? Well, the secret is fire. It all comes down to this one simple, fundamental rule. When you heat something up, you're giving its molecules more energy. They start jiggling around more and more, and they push their neighbors farther away. The result? The entire object gets bigger. So that blacksmith's ring expands just enough to slide onto the wheel. And then, as it cools down, it shrinks and grips that wheel with a force that is just unbelievable. And depending on the object, we can think about this expansion in a few different ways. For something long and skinny like a wire, we mostly care about how its length changes. That's linear expansion. For a flat sheet of metal, we'd look at how its area grows. And for a big solid block, we'd talk about its total volume increasing.
Okay, here it is, the classic exam question that is designed to trick you. You have a metal plate with a hole in it. What happens to the hole when you heat the plate up? Now, your gut might tell you the metal expands inward and makes the hole smaller, but that's wrong. The entire sheet expands in every direction, kind of like zooming in on a photograph. Every single part gets bigger, and that includes the hole itself. Don't forget that one.
All right, you've soaked up all the theory. So let's do a quick power-up round to make sure you're totally ready for any exam questions that come your way. Okay, first up, let's test that conversion skill. So you've got 20 degrees Celsius. Remember that formula? You just add 273.15, which gives you 293.15 Kelvin. Simple, right? But it's an absolutely essential skill to have down. For this one, think back to the ideal gas law, or even just Charles's law. When you take the balloon outside, the temperature of the gas inside it is going to drop, right? And since volume is directly tied to temperature, what's going to happen? The volume has to decrease. The balloon will actually shrink. So let's wrap this all up. If you're going to write down just a few key things to remember for your exam, make it these 4 points. 1. Temperature is a property, heat is a flow. 2. The Kelvin scale starts at absolute 0. 3. Know the ideal gas law. And 4. Things get bigger when they're hot. Master these and you'll be in fantastic shape. And look, this stuff isn't just for your exams. It is literally all around you. This is the physics that explains why the wind at the beach reverses direction at night. It's why food cooks way faster in a pressure cooker. Once you start looking, you'll see the physics of heat is shaping your world in all these incredible ways that you can now totally understand. What will you notice first?